Thank you. So before we go on with my talk, I just want to give you this piece of news. I mean, if, like me, you look at space news, this is news from last week. It's old news already. But if you don't, I think this is pretty cool. So this one is an asteroid that just been impacted by a human-made spacecraft. Why we want to smack a $300 million spacecraft in an asteroid? In fact, the reason is very simple. It's like if this bit here, it's 160 meters in diameter, would hurl toward Earth, that would be catastrophic if it would impact, like especially on Perth, for example, for us, right? We wouldn't want that. So we would want to do something for it. And NASA is very conscious that it can happen. It happened in the past. We got impact crater everywhere. We know that. So what they did is they smack a probe to see if, just by smacking a small probe, we can nudge the asteroid enough so it would avoid a collision with Earth. Now, nowhere this asteroid is going to collide with us. Okay, don't worry at all. It was just a test, but it was a success. That's the explosion right here. It's hard to distinguish where is what, but that's, yeah, that worked very well. So they impacted this tiny probe, it's called DART, on this moon. It's called Dimorphos, and this one is in fact a moon of Didymos, a bigger asteroid, so it just goes around here. And I thought that was pretty cool. So that's one step toward being safer from asteroid threat. Now the one I'm going to talk about today is a bit different. It's much, much bigger. If this one slams on us, this is game over. There's just no way we can push it. But it won't. It stays happily in the asteroid belt. This is my favorite asteroid of all time, and I'm going to justify why. This is asteroid 4 Vesta, okay? The volcanic asteroid. And that's why I like it so much. All right, so we're going to talk about volcanism on this asteroid, the crustal cooling, and also something which is I find interesting is the impact history throughout the history of the solar system itself. Okay, so what are we going to talk about? We're going to talk about Vesta because I'm pretty sure most of you are not familiar with Vesta. I'm going to talk about the technique I'm using to investigate Vesta. A lot of many people before me, they worked on Vesta. Okay, but they didn't necessarily use the same technique and to the same level of precision and stuff. So we learned a lot by applying that. But I want to explain to you how that works a bit. So there's going to be a tiny part that is going to be a bit more technical. Then we're going to talk about basaltic rock and asteroid eruption. Pretty cool. And collisions between asteroids as well. Okay, there's several stories that can be told by the argon technique. Now that's asteroid Vesta. Okay, we get a really, it's a true image. It's not like a, like a fake one. It's true, and that's the scale right here. Okay. So Vesta is a rocky asteroid. It's been discovered a long time ago. And if you always wonder why there's number in front of asteroid like that, that's their order of discovery. Vesta is the 4th asteroid that has been discovered. And back in the old days, they were like, wow, this is really cool. There's so many asteroids between Mars and Jupiter. There must be a planet that has exploded, right? There used to be the theory. We know it's not true. It's a planet that never agglomerated. In fact, never been a planet then. But the previous theory was pretty cool. That's sad it's not true. Otherwise, that would be awesome. It's fairly big, 525 kilometers in diameter. But what does big mean in this case, right? Because when you see image like that, in the background of space, okay, it looks like a planet to me. Well, that's the scale right here. So I'm originally from France, but this is an absolute coincidence that it's compared to France. I swear to you, I didn't make this image. Look, I mean, it's written where I took it. This is Ceres, okay? This is a dwarf planet. This is Vesta. This is the biggest asteroid. Now, this is all semantic, Okay, there's a continuum between everything. But the difference is it's completely round. Okay, it's rounded. This one is not. And it could have been rounded, but it's been beheaded by a huge impact. So therefore, it's still an asteroid. And why I like it the best? Because it's entirely covered by my favorite rock type, basalts. That's what I like the most. It's not pretty, it's ugly in fact, right? There's nothing happening with the basalts, but it tells so much about the history of a planet that once you know how to read it, you get to love it. Now, we know a lot about Vesta, but most of what we know is not by using a telescope and looking at it. Now, sure, it's pretty, but in fact, we get samples from Vesta. At least we think they are from Vesta, you know. They are called the HED clan, so HED stands from Howardite, eucrite, and Diogenite. And I'm going to talk especially about those two. So what does that mean? You just need a simple translation. Eucrite means basalt or gabbro, right? And Diogenite means pyroxenite. The Howardite, don't worry about it. This is regolith. This is a mixture between the two. So you crush the two rocks, you mix them together like the moon. You know, you get the regolith at the surface. This is what it is, except it's hard. So it's a rock. That's Howardite. Now, compared to the moon, we get 448 kilos of rocks. Most of them brought back directly by astronaut. Here, we get 1.3 tons of rock, 3 times more. So, well, how do we know they are from Vesta? We know they're all from the same asteroid body because they all have the same oxygen composition. I'm not going to go into detail into this graph how that works, but you get to know that oxygen 17, like that, and especially when you use it in delta form, it really tells you it's a signature, it's a fingerprint if you want. And all those have the same fingerprint. So therefore we conclude they come from the same asteroid, and they are very complementary in their chemistry as well. How do we know they are from Vesta? Because Vesta is the only one with this basaltic surface. But there's always the possibility that there was an asteroid before, like Vesta, that get completely exploded and shattered. And they all come from this. We will not be able to rule that out until we measure the oxygen composition at the surface of Vesta. But whatever story we come up with, we just would have to do, hey, remove Vesta by whatever new name. That wouldn't change anything. That's still the same story. And it's a good story, so be it. How do you obtain basalts on an asteroid? Well, it's fairly simple. You know how Earth forms, you're all geologists, right? So you have an accretion, and then you get differentiation where you have a core, a mantle, and a crust. And this crust at the beginning of Earth was also very basaltic. And then after we got granite and stuff, because we had subduction, a lot of process happening. Vesta, switch off, it's super small, right? So how long is it going to keep its heat? Not that long. So it just produces a basaltic crust and stop there. But there was more. Recently, NASA sent a probe, and that's where we get all those pretty pictures, the one in the background. This one here, you see how sharp it is. So down went to Vesta and Ceres and took a lot of pictures, gravity measurement, elevation measurement, all that. Stay a year at Vesta before going to Ceres. So that's the good thing. We can correlate, compare all the information we get with the HED and implement that on all the information we get on Vesta. And that's of a better story. It's like you go in the field in the Gilgard Craton and you sample a rock and you know where it comes from. Therefore, you can put a better story. Then somebody brings you a rock in your lab, say, hey, can you tell me the story of this rock? Yeah, okay, you're going to try to piece something together, but that's a bit harder. So the fact that we can correlate things, it's pretty cool. So yeah, it looks something like that. You get Vesta, you get the metallic core, the stony mantle, and the basaltic crust. Our basalts right here, okay, sit at the top. Then we get the gabbro, maybe a few intrusion, a bit deeper. And we get something very interesting. Now, Vesta is an asteroid where there's metamorphism. Okay, so you think about metamorphism, immediately you're like, okay, mountain collision, huge pressure, you know, glaucophane type mineral, not at all. In this case, there's zero pressure. In fact, the pressure in the center of this asteroid is really not much. Can't remember, but it's a matter of kilobar, it's nothing. So pressure plays no role, but if you accumulate enough heat, so either from the mantle or from eruption on top of eruption, then you metamorphose your rock and you create a granulite. Granulite from a gabbro, okay, same composition. And then you get the pyroxenite. And I'm pretty sure, and especially since I made the color green like that, you're like, oh, okay, that's piece of the mantle. But that doesn't work like that. Because what is the main mineral when you think about peridotite and mantle rock? Olivine, thank you. Absolutely. Well, there's no olivine right here. It's pyroxenite, pure pyroxene. Now, some of them very rarely have olivine, but most of them don't. So what we think is they still belong to the crust, but they could belong to the top of the mantle. You know, there's some debate. There's plenty of questions we don't know about Vesta. So what's the structure of the crust? Is it like a thin basaltic crust with some pyroxene cumulate at the base and then the olivine-rich mantle, or a thick basaltic crust with a lot of pyroxenite infusion? We just don't know. Okay. Was there a magma ocean? Was there several mini magma ocean or lake? Or, you know, a lot of it was not molten? We don't know. People, they think they know. You go in conference room, they're going to tell you their model is the best. This is this one. But then you go to the next talk, and the previous model was completely wrong, and their model is better. So to me, that tells me we still don't know. There's plenty of stuff unanswered about Vesta and its internal structure. And why, before I go to the argon bit, why we want to know that? Well, for the sake of knowing, I'm interested. Like I say, it's my favorite asteroid. I need to know more about it. It's visceral inside me. I need to know. But if you're only interested by the Earth, then you also want to know. Why? Because this is a really simple system. It's a small asteroid, switch up very early, no complex metamorphism, just a heat contact metamorphism. So if you learn how Vesta works, then you can extrapolate that to early Earth, which was very similar to that. Okay? So that's important to study those microplanets. All right, so what I'm going to use to study Vesta is the argon-argon technique. This is my specialty. So what we do is simply measure age of rocks. It's derived from the decay of potassium into argon. We irradiate the sample in the core of a nuclear reactor, and we measure that with expensive machine, if you want. So this technique exists since 50 years. It just gets better and better with the years because we get better and better machine, more precision. More precision lead to better story. There's about 50 labs in the world, but as I said, 25 of them are viable, working. The other one, they're just a machine sitting in a room doing nothing. And there's 4 working labs in Australia. So in terms of density of lab per inhabitant, we're one of the most dense in the world. And believe it or not, every lab is ultra busy. We're not competing against each other. We're all friends, you know. And that's a good thing. So we created a network, we exchange things and stuff. So in Australia, the argon-argon scene is pretty happy. Now, I said there's 25 working labs, but working on planetary material, not much, almost nothing. In fact, there were a few in NASA, but they all shut down. So much that NASA send the stuff to Perth, in fact, right? Not everybody, but many NASA scientists do that because people don't do that for obscure reason to me. Okay, so we get 2 instruments. Some old generation one has been decommissioned. We get some new one, new generation, and in this new technology is extremely important. Okay, why is that? Let me show you. So before it was single collector, now it's multi-collector, but let's look at some results. So this is age. It happens to be from Vesta, actually. And this was with the old machine, okay? And thanks to the new generation of machine, we achieve precision like that. So that is error bar. So plus minus, so this age is 45, 26, plus minus 23. The plus minus is what's important here. And with the new generation of machine, plus minus 8. And the fact that I put 3 of them, it was 3 tests on different configuration. But it also shows something. It's like, for me, it's much faster now to generate data. In fact, 3 times faster than before. Okay? So you generate more data, they are more precise. So you combine all of them, they give the same age, and you reach a precision which is insane compared to what was available before. Okay? A lot of people would kill for this precision, and we can achieve that with the argon technique. So the final age here in this case was 4531, 4.531 billion, plus minus 5 million. But there's also some crazy stuff we can do with it. That's Itokawa, and the Japanese, I'm not going to go in story, it's an entirely different story in itself, but they brought back particle from this asteroid. Particle really, really tiny. Look at the scale here, 20 microns, so that's what, 80 micron in radius? And that, thanks to the new generation of machine, we could measure the age on a single particle like that, with a precision at, what's that? 40 to 19 plus minus 35 million. So 4.2 billion plus minus 35 billion, tiny stuff like that. So I could speak hours about this machine, but let's look at the result that what we can get with it. But that really changed everything. Now, one thing I want to, before we go in the result, how do we look at those results? What we do is we simply put a crystal in the machine and we tap it with the laser. We hit it with the laser. And 500 degree, we increase the laser power, 600 degree, 700 degree. We peel it like an onion. See, I call it an onion. We peel the layer. Each temperature is higher, so I peel my mineral like an onion. And if I'm lucky, or I did a good sample preparation, the stars align, and rather should I say, all the answers align. They all give the same answer. It's a closed system. I get a really good age. For example, this was for basalts from a large volcanic province at 201 million years old on plagioclase. Now, sometimes the stars don't align and the system has been opened, either by alteration or in space by impact, and you get some nasty stuff like that. Okay, so what's the age of that? Well, that's supposed to be that, but it's been perturbed open system, so we don't know. If we use only this sample, we wouldn't know. We just know because all the others are here. So we know it's been compromised. And I think you see where I'm going with that. It's like you get to use good age. Otherwise, you get a wrong answer. Or maybe the age is that, or maybe that, or maybe that. Doesn't work. You want that. Oh, the age is that. Yep, we all agree. Not convinced? You think I'm over harsh about bad data? Okay, let's have a look. This is on Earth. This was a really interesting theory. It was called the late Triassic multiple impact theory. So some people noticed that some of the age of terrestrial impact crater were fairly similar within uncertainty. Big uncertainty, but they were all overlapping. So they were like, they all impacted at the same times. So like a chain of impact. I don't know if you've seen, it was in the 90s, you had a comet Shoemaker-Levy that impacted Jupiter, right? And that was a string of impact. That was pretty spectacular. So people thought it was exactly the same here. Boom, boom, boom for the main one. And then those one, they were in small circles, so that's why they impact on the side. All at the same time. Huge science paper. You know science paper, they like the stuff that are, yeah, yeah. No, I'm not going to talk about it. But we redated all that using the approach I mentioned before, making sure the data is solid, the data are clear, and that's what we got. So you take that, this theory, you just put it in the trash. It belongs to the, the theory that never happened. And in fact, it should have never happened. When you have imprecision like that, you can't conclude. You need to work on it, but people prefer to go to the big story first and do the analysis 30 years later, which is what we did, all different. So that's why it's so important, precision and especially accuracy, to avoid to do things like that. And we're all guilty of having done stuff like that. I mean, I won't even blame those people. I mean, you know. All right, okay, before we go back to Vesta, one last slide. Basalt, what is basalt? You all know what is basalt. I don't want to insult you. You know what is basalt. But what I want to really point out about basalt, it's a mixture of plagioclase, pyroxene, and ground mass, okay, more or less, with different proportion. And all those three phases are datable with argon-argon. Yeah, you think only plagioclase and ground mass? No, we can date pyroxene too, no problem, too easy, in fact. So two important points I want to make. We're going to look at the history before 4.45 billion years. We're going to look at the early volcanic history, igneous activity, and cooling of the crust, the very beginning of this asteroid, this microplanet, or wannabe planet. And then we're going to look at the impact history from 4.56 to yesterday. So let's get started. Part number one, the very, very old history. What question do we have before we provide some answer? So how long did it take to build the crust? How long the system was volcanically active? When did it shut down? How long did it take to cool down the crust? Because this is all related. And we can even try to address some other side question, like, you remember I mentioned we don't know the structure of the crust. Can we gain some information from the argon system about that? Are the autopyroxene deep in the crust? Are they like intrusion? Yeah, let's have a look. Let's see what the argon system can tell us about that. So what I did, oh, no, so sorry. No, I'm not going to take the credit for that. What somebody else did was to synthesize all the age existing on Vesta before, which is a great way for me when I started working on that. Oh, somebody did all the job. This is excellent. I didn't like it. I didn't like it because the criteria were too loose. People don't want to offend their colleague. I'm going to take your age because I like you. You know, we all work together. I don't mind. I'm going to offend people. So what I did is like filter that by quality, but also precision, because this person chose to filter the data with precision plus minus 50 million. Okay? But when you study the first 50 million years old, and you get a precision of plus minus 50 million, that's 100 million. It just doesn't work, right? It just belongs to it or not. It's a binary information, not really useful. So I decided to filter, I could be even harsher than that, but like, you know, I decided to filter by plus minus 20 and only accurate age, the one that reflects a closed system. So that's the published age, right? Fairly old, all around 460, I'm going to read them like that, 4560, 4550, all on zircon mostly. Yeah, no, almost all of them. So we decided to add a few of our own. And remember what I said, if you want a good age, you want it to be flat. And that's fairly flat to me. So I was really happy with the result we got. A lot of them, so we did on plagioclase, pyroxene, ground mass, and we did many, many aliquots for each sample we were investigating. They're just too precious to do one analysis and that's it. You want to maximize it. So we arrive with decent precision. This age is 4520 plus minus 5, 4531 plus minus 6. Very happy with the level of precision. Okay, and on all of them, we did all that. Okay, I just want to compare, just to, you know, put the nail in the coffin. I want to compare what people had before and what we had now. That's data before. It's very wavy. You don't know where to put the age. You shouldn't put an age at all on that. And that's what we get, you know. On different phase, giving the same age, much more precise. Same here with a different system. Lead, complete scatter. I would never draw a line through that, but you know, people did it. they get an age at 4.48. We redid it. Sometimes it doesn't work, but when it does, 4533, much older, much more precise, much better. But you're going to think that I don't like uranium lead when I say things like that. I love uranium lead. This is, I work with some friend that do uranium lead as well. So on this granulite, that was the most metamorphosed rock on Vesta. We combined system, and that's the best stuff you can do in geochronology. You combine multiple systems. Now, when you have only basalt, this is hard to do because you can do only argon, basically. But when you get a system that contains zircon and other phase, then you can do a whole lot of dating. So uranium lead zircon, uranium lead oxide, they even do uranium lead on plagioclase, pyroxene, and apatite for dating. And then, of course, I did argon-argon on plagioclase. And then we obtain a very consistent cooling age, right? Because something I didn't mention, but when the system erupts, what you measure in instantaneous age. It erupts, cool down, that's it, that's the age. But when your system cool down over millions and millions of years, then different minerals will start to record at different time. It's what we do in thermochronology when we do metamorphism. So here zircon closed the first, and then you get, can't read, lead in oxide, in pyroxene, in apatite, and the last one to close was argon. So that's why it's younger in this graph. And all that gives us is a nice cooling age of 11 degrees per million year, and very consistent. And the last thing we did was on the Diogenite, the pyroxenite. So people would argue there's no potassium in pyroxene. I disagree. I disagree. In space, I disagree on Earth. We routinely date pure pyroxene, okay? So a lot of them didn't work. So when it doesn't work, it's not other people, it doesn't work. For me, it doesn't work a lot as well, but sometimes it does work. And we had a very beautiful age, which was much, much younger. Much younger. So we think it cooled down much, much later. And that's some interesting information. Let's put that together, shall we, in a graph. Now, if you don't like graph, don't worry. I got a little synthetical diagram after. So feel free to skip that if you're not into graph. So that's the result before. That is an age we obtained on the youngest eruption so far. I'm not saying there's nothing younger in terms of eruption, but that's the youngest we know. Okay, so we know that the Vesta was still erupting 35 million years after it started to accumulate. And people thought it stopped at 45, 50. So that's 20 million years after it keeps erupting. We dated magma chambers, so those ones, they are Pluton. They were still active at this time as well, same age. That was something I was excited because that was the most precise age that I had, both on plagioclase and pyroxene. Turns out it was just an impact. So sorry for impact people when I say just in impact. I also love impact, but in this case, in this particular story, that was just in impact. That's what it was. And then
doors over there, man.
But don't worry, I get the second part only about impact, so no problem. And that was the cooling. So that was the metamorphosed basalt, the granulite, okay? And we had a nice cooling age on that. And then we get agate that contained everything, one in all, where we also had a cooling age. Cooling age, different because different level in the crust. And then we got the Diogenite, much, much younger, much slower cooling rate. Cool story as well. Now that's my diagram. I wish I could tell you, hey, look, this is my 6 years old that did this drawing, you know, you get to forgive him, but it's me. I'm just not an artist. I don't have that in me. But I hope it does the trick to explain things. The youngest eruption we talked about, the shallow intrusion, you know, all at the same age, 45, 30, indicating that this was still magmatically active. And you know what's already also cool in this one? It recorded a magnetic field. So there was, again, two types of people. No, the magnetic field stopped 5 million years before agglomeration. No, it continued for tens of millions of years. Well, we know it continued for tens of millions of years because this one recorded the magnetic field and it's young. And then we get the granulitic one, the metamorphosed one that are much deeper, 15 kilometer depth, and slowly cool. And then we get Agul, the one with the big juicy zircon that cooled even later than that. So it was even deeper. So now we start to have the structure of the crust. And then we get our Diogenite. And because of the very slow cooling, they must be very deep. But we still don't know if they're part of a giant layer or part of plutonic intrusion. Now, if you ask my opinion, and this is all it is, I would bet on that. But not more than a coffee, right? Because after that, now, remember I showed you that, and some people think it's a very thick crust with the diogenic Pluton. Some people, no, it's a very thin crust. And look, at 40 kilometers, you must have the mantle. Well, not really, because we calculate at 60 kilometers, you must have those Diogenites. So they need to extend that. If that is true, it needs to be extended. It doesn't work like that. Again, I believe this one is more true. Makes more sense when you look at chemistry and stuff like that. Can I stay, Aaron? Yeah? No?
A few minutes.
Impact, of course, you look at this and you see there's plenty of impact. Do you know how this is called? Anybody knows? The snowman. Really? It's been nicknamed the snowman, but everybody used it. It looks like it. It's 3 impact. Did they happen at the same times or not? Well, I hope you learn a lesson with the Triassic stuff, right? We don't know until we did them. So now for that, we're going to look at brecciated rock. So brecciated rock, they are a bit different. The one I showed you before, they are pristine basalt. They're beautiful. You would find them on us, you would think, I get basalts. But those ones, they are just a mixture of a lot of components. Some of them, they are polymiced, so a bit of basalts from different places. Some are monomiced. It's all the same basalts coming from the same place, but have been rearranged clearly as a rock agglomerated together and compact. So in other words, have been generated by impact. So they must record impact. Okay. So what we want is to learn about the bombardment history of Vesta and compare that to, for example, bombardment history in the asteroid belt or in the moon or other body in the solar system. And again, if you look at the topographic map, you can see that there's really, really big crater around. But the biggest, they are on the South Pole. Okay? They are called Rhea Silvia, this one, the biggest, and Venenia. And this one is so big, that's almost the diameter of the entire asteroid. Remember, it's an image that has been, a bit shifted so we can have more view, a bit bird view if you want. But if you look at that, this is the central peak. It's almost been beheaded. And that cost it the dwarf planet title, right? How good we are with semantic and, classification for absolutely no reason. That's why I teach to my first year student. I tell them, look, it's a continuum, but we like to pigeonhole things. So 2 giant impact. Maybe the meteor, the HED recorded that. So, okay, I was not, whereas what I presented you before, nobody did, okay? But that people did before. So they tried to look at impact ages. And they had a lot, so 36 ages, right? So that's what they obtained. Now, if you remember what I showed you about things need to be flat to be good, well, let me highlight that for you. Does that look flat to you? Well, not really. So what it tells us, it's open system. And that happened quite frequently in impact. You have a mixture between the age of origin, the origin age of the rock, so around 4.5 something, and the impact. And then those spectrum, they're everything in between, but you can't tell anything more than, yeah, it's in between, it's intermediate. So that's really not satisfying. For somebody like me, I've seen so many people fall in the trap and at the end it's all wrong. I don't like it. So what we want is something like that. Again, flat. We know, we all agree, this is the edge, it's a closed system. Now, before you think I only criticize other people, this is our edge as well. So we generate that, and you can see how we put like, oh, okay, yeah, if you tempted to put an edge here, it's still better than some of those stuff, but if you do that, and we date it in a different aliquot, you can see that this one, they're supposed to have the same age. They are melt rock, not a breccia in this case. It's about 100 million years younger than this one. So if you put ages in the wrong place of a spectrum, you get the wrong answer. You have to be really careful with that. So here, it's a much better answer. It contains much more of the total stuff. So we have very severe criteria. Some people would even throw insult at me because I'm so severe with the criteria, but it gets the job done in terms of accuracy and getting a right story. Now, when we did our data, we filtered the old data. Like one of the reviewers producing the old data was really not happy in his review of my paper. Yeah, you redo stuff that has been done. Okay, whatever. So but he was right for one thing. That we remove tons of his ages, but we just bring 3 new ages and 2 on the same rock. But that's a breccia, so that's okay. They can record different stuff in breccia. It's expected. So that was okay, but that's not enough to build a story, right? Having too few data compared to the story is supposed to be over billions of years. So we had 1 plagioclase, 2 ground mass. We had pyroxene too, but that's at this stage that we realized that pyroxene record tiny impact. That record big impact, that record tiny impact. I don't want to go into detail. You get to trust me on that, but if you want to know why, I can explain to you with a very nice and heavy Arrhenius plot. Now that is my own adventure with my colleague, Trudy, through dating those rocks. This is terrible. This is just not good. Yeah, well, you know, it's not other people were bad and with the superhero of argon dating, we fail massively too. But we also succeed because we put a lot of those samples. So here, you need to use brute force. Many samples will fail. But there's some that are going to work well. And if you use brute force, you will find them. That's much easier when it's your lab, right? Because you don't need to pay for the analysis and this and that, so you can go doing this stuff. So we generate a lot of data. That's just an example of a few, but we had 30 new aliquot that yielded plateau ages like that. Pretty cool, pretty solid, fairly precise. And we had something like that. Okay, that's interesting. All a concentration of, that is several meteorites, and they are polemic breccia, so they contain components that have nothing to do with each other. And despite that, they give a very consistent age here. So we think that it was a big impact. And then we get nothing here in our new results and a continuum here. Now let's have a look and let's see what it means. We think because different sample, different meteorites unrelated and stuff, and they all tell that something happened at 4.500 plus minus 4. So, okay, that's probably a big impact somewhere. Which impact it is, I have no idea. Now that's where speculation comes. While we all want it to be Venenia or Rhea Silvia, one of the two. Yeah, sure, it's possible. And of course we put that in the paper, but we didn't say, it's that. We said, it could be that. That would be cool if it's that. We don't know, okay? The only way we can know is by going there with a probe and sampling stuff and bringing them back, and then I'll tell you. And then there's something interesting. It's like you get a gap here. So I shaded those one. This one is an apatite age, but they can be very intermediate, so you get to be careful with those ones. This one is an anomalous achondrite. That means it belongs to a different parent body. This one was a lucky plateau. But that doesn't mean they are not real. That means they are suspicious. Okay, you get to be careful. So there was two possible stories. Well, in fact, you get a continuum. It's just been erased. Because when you unpack that, you erase what's there. Or it never happened in this batch. And the batch we have only recorded that, right? So I love graph like that. They explain things better than me trying to explain number. That has been drawn by my Argon Lab technician. She is an artist. She can do things like that. You notice the difference between when she does it and when I do it before, right? There's a bit more art into it. So scenario one, you get a continuous bombardment. You always have bombardment on planets. It's not a surprise. We know that already. But at 3.85 here, you get a big impact that carves a fresh new surface. So all that goes somewhere else to be lost forever. And on this surface, you get impact during 400 million years. And then a big one that ejects everything. And that ejector goes into one of those rubble pie type asteroid and drift in the solar system, being impacted regularly and bringing us the HED. So that's why the history of HED is only recording those ages. Nothing after. Okay, there's nothing younger than that. Whereas we know that Vesta is impacted from 4.56 to now. Second scenario, it's a continuous bombardment, but like I said, the one that happened at the beginning, younger, they're just simply eroded by the younger one. It's called gardening a bit. You know, it's a bit like what's happening on the moon for those who know the story. And then ultimately at 3.47, everything is ejected and goes into this rubble pile. And why I want to say it's a rubble pile? Most of the asteroids we see now, when we image them, they turn out to be a rubble pile. We thought that they were a solid chunk of rock, but it turns out they're just an agglomerate of rock. And the interesting things about this agglomerate of rocks, it works like a cushion. So if you bombard the cushion, it just, you know, it takes the shock. So it doesn't affect the rock and the mineral is in it. Compared to a hard rock, that's going to take the shock, heat up, and reset the mineral. That's one of the last slides, in fact, before my conclusion. So that's the stuff I'm working on right now. I'm writing the paper. That's the thing I did before coming here. I look at the age recorded by the Diogenite, the pyroxenite, but the impact one, not the old one that I mentioned before. And that's the one I just showed you, and that's the one recorded by the pyroxene. And what's amazing, there are two different populations. They are not even overlapping. And that I had to scratch my head. I'm like, but why is that much younger? So there's just two possible explanations comes to mind. Feel free if you get another one to email me. If you want to quote a ship, if it's a good one. Yeah, you know what? Yeah, sure, no problem. If it's better than mine. So I think what could have happened is that, okay, we had this big eruption right here. And then the same story happened. But now we're much deeper. So we get, you know, the eucrites, they are safe here. They drift by themselves. Now we impact this surface much deeper, contain Diogenite intrusion, and then much later on, you know, few tens of millions of years or whatever, there's a big impact that ejected those rocks and bring those things. But what I don't like about that is even there, because we know it's covered by basalts, I should have eucrite of this age. And, you know, I don't. So, or they were ejected at the same times. Okay, they're part of the same rubble pile right here. But remember what I said before? Probably not, so I'm going to remind you that the pyroxene is not recording the same thing than the plagioclase. Just a tiny impact will reset my pyroxene. You need a big, hot impact to reset plagioclase in eucrite. So, in essence, it's a continuum story simply because you interrogate apple and oranges, and they have different flavor. Okay? All right, so that's all about as to say. Vesta was volcanically active 45-31 million, and the core was still molten because we know we have a magnetic field. We measured the cooling of the crust the first time. Before it was all about models that vary by hundreds of degrees, actually. We know that the mantle boundary must be deeper than 60 kilometers. That's a minimum. Very large impact recorded at 4.50, maybe one of the two. I can always dream about that. I don't know. And that the eucrite recorded a period of bombardment of only 400 million years. Only that, so we get a nice theory to explain that. And then that the pyroxenite recorded some different impact, and that's what I'm working on now. And that's about it. Thank you very much for your attention.